All right, can you all hear me? Okay, so so from this point on in the course, we're going to be looking at three technologies. One I'm going to introduce, that's the superconducting circuits or circuit QED. That's what we're going to do today. Today and next week. After that, you're going to have the trapped ions system. You're going to have 2 hours on that. And after that, the final lesson will be 2 hours on neutral atoms. Now, the distinctive feature the distinctive feature of these three technologies is really the fact that these three technologies are true contenders for realization of a quantum computer. If ever there was one, if ever we're realizing one, I would say that these are the three leading technologies. There's someone with a mic on, and I'm hearing background noises. There, whoever it was, thank you. So you're really going to get a look or an introduction into these three leading technologies. And each technology, as you will see, has its strengths and downsides. You will kind of have to dig into it. And really the purpose of these three lectures are to introduce you to each of these technologies, so then you can later on just go ahead and read papers in these fields and understand what is going on and look at these details. Okay? So what I'll do, I'm going to pull up now. Can everybody see my screen? This presentation here?
Yes.
Okay, great. So you can see the presentation. Okay, great. So you can see this presentation. So I'm going to start off with the circuit QED. And usually when I give the talk about circuit QED, I start off with this slide over here. The next one, not this one, the next one. Okay. And the purpose of this next slide, this is just a Google search, Google image search, where you type quantum computer, and this is what you get. And what you're seeing in this picture here is the inside of dilution refrigerators. What the search, and you got to really scroll down, and I keep repeating this in many of my talks. You got to really scroll down to find something else that is not a dilution refrigerator. And this dilution refrigerator is where you put the superconducting circuits inside. You want to cool them down to low temperatures. And the reason that this shows up is basically this technology is currently considered the most advanced and the most promising for realizing quantum computers. It also tells you that it's highly hyped with respect to the other technologies. And it also tells you what is a third thing that you get from seeing these pictures? It is the most photogenic. Okay, you can take nice, pretty pictures. You see these nice golden chandeliers. It makes nicer pictures than atom traps. Okay, that's basically what it tells you. Okay, and these nice golden chandeliers are really, this is a commercial product. You have $500,000 in your pocket. You can just take them out and buy. Maybe the bigger ones cost $1 million, but that's roughly the price. You can even buy them with most of the wiring. And all of it is just a big refrigerator. And if you look at this picture over here, at the bottom in the middle of this refrigerator, there's this silvery thing. That's some shielding can. And inside the shielding can is where an experiment actually sits. Okay? So what does a lab look like? What does a circuit QED lab look like? Just to give you a sense of what we're talking about. Because if I say atoms and atoms interacting with fields, we already talked about cavity QED and you know what we're talking about. But here I'm telling you about a platform which is circuits. Okay, we're talking about printed circuits. And the question is, what are these printed circuits? Okay, and how are they quantum? Okay. So a lab looks basically like this, what you're seeing here. So we're talking about circuits that operate at gigahertz frequencies. So they can absorb and emit radiation, photons, at gigahertz frequencies. Gigahertz, just for a scale, 20 gigahertz is about 1 Kelvin. So we're talking about very, very, very low energies. Okay. Many, many orders of magnitude below visible light, of course. This is why we don't get cancer from cell phones, okay, or direct cancer. These circuits are cooled down to millikelvin temperature because you want to be well below these gigahertz frequencies. Okay, otherwise you get a thermal population. The size of these circuits, and this is one of the more distinct features of this, is that the size of these circuits are about millimeters. This is huge, okay? This is about 10 to the 23 atoms we're talking about. The feature size of these circuits go down to nanometers, so about hundreds of nanometers. But the size of the circuit is about a millimeter. And these circuits, you basically take them and you mount them right here. Can everybody see my mouse? Yeah? Just do a V or something. Yeah, okay. And you mount them inside the dilution refrigerators, and you put them inside. You cool them down inside these refrigerators, and we have essentially commercial microwave electronics, which are relatively developed because of all the telecom industry. You buy them off the shelf, and with these electronics, you control these circuits. So this is kind of like just to give you a picture of what a lab looks like. Now, the main concept behind these circuits, and this is why it is very nice to give this slide and this explanation to someone who knows what cavity QED is. That's on the right over here. Okay, so we talked about atoms, and you understand how you take these circular Rydberg atoms and they fly through the cavity mode, right, and interact, and you get the Jaynes-Cummings Hamiltonian. In circuit QED, what is happening is that you're building these circuits. They're made out of superconductors. And you basically have these simple circuit elements, capacitors, inductors, and another element which we'll discuss, a Josephson junction. And each circuit, which is about a millimeter size, maybe half a millimeter size and so on, basically acts like an atom. So there are quantized energy levels, and it acts like an atom. And what you want to do is you take the circuit, just like in cavity QED, where you take the atom and you put it in the cavity to interact with light. You take the circuit and you put it in the cavity to interact with light. Okay? This is the idea. So you have your atom, which has these unharmonic levels, and you have some distinct transition, which you call G and E. If you remember, in our circular Rydberg atoms, we had circular Rydberg 50 and 51. That was the qubit of choice for the Serge-Haroche experiments. And neutral atoms might have laser transition frequencies and so on. But in the same way that you can think of an atom in two-level systems, you're building a circuit, and we're going to understand how this circuit is quantized, but you're building a circuit where you have quantized energy levels, and you pick two of these quantized energy levels, and typically the transition frequencies of these energy levels are in the gigahertz range, the low gigahertz range, 5, 7, somewhere between 4 and 8 gigahertz. And this forms the qubit. Okay. Can anyone guess why gigahertz frequencies? Why the low gigahertz frequencies? Anyone? No? All right. 4? Okay, well, the reason is basically because we want to control the quantum computer with a cell phone. No, that was a joke. That's not real. I mean, essentially, the microwave controllers are very smart cell phones, right? Very precise, but you can't control it with a cell phone. That was a joke. But it is basically you want low energies. You know what? We'll explain the quantization of circuits, and then I'll get back to this. Okay, maybe it'll be better to explain it then. But basically, you want to stay well below the energies of the superconductor. So superconductor becomes superconducting below a certain temperature, so you don't want to go to energies beyond that where it will not be superconducting anymore. But I'll be more precise about that maybe in the next section. But the concept here, and what you're going to see, and we're going to do this more rigorously than I usually give this talk, the idea is that taking circuit elements like capacitors, inductors, and Josephson junctions, these are marked here by X's, and these shunting junctions you can think of as inductors. By playing with these circuits and these topologies, you can get different potentials and different quantized energy levels. Okay, so this is mainly what we're going to be discussing today, how we get this. Okay, if you just take the simplest example, take an LC oscillator, and we're going to see this, you just get in a harmonic oscillator. You've done regular electronics. You know that an LC oscillator just gives you a frequency. We're going to see how to quantize that, and then you get a quantized harmonic oscillator. Okay, and then we're going to see how the Josephson junction allows us to get something that is not harmonic, meaning the energy levels are not equidistant, and then we can choose, let's say, 2 levels out of that to represent our qubit. Okay? And so the whole idea of this platform is really you take these circuits, and you have many of them, and each of these little circuits, or you have one circuit with many of them, but each of these is this artificial atom, and this is your circuit Hamiltonian, and you couple it to a cavity, and this is your field, and the field can interact with a cavity for control, and we're going to see also the details of that. And then you have this whole Hilbert space of the circuit, which can be a 2-level system, a few-level system, just like an atom, interacting with a cavity. And this whole Hilbert space, you can actually gain full control of. Another distinct feature that you're going to see about the system is that it has a very, very strong coupling. I showed this to you last week with that light-matter interaction diagram that I showed you, where the system really sits very deep into the strong dispersive regime. And it gives us a lot of versatility, and in the sense that you can encode information really anywhere you want in this Hilbert space. And you're going to see the same property, by the way, in trapped ions too. And it basically means that you can take your qubit and you can encode it in the trivial way in the 2 levels of your artificial atom. You can do that. That's a trivial choice. You can also take the qubit and encode it in 2 levels of the cavity mode. We saw that already in cavity QED, for example. But you can also gain control over more levels and do a logical encoding over many levels. If you remember at the very, very first lecture that I gave you, we talked a little bit about redundant encoding and how you could do error correction. I gave the simple example of encoding, I gave the classical example of encoding 1 bit, which is 0, 1, in several bits, and then you do a majority vote to correct that. So the essence of error correction and logical encoding is having a redundancy. And you can use the redundancy of the cavity, of the many photon levels of the cavity, to help to do error correction. Now, I probably won't get to talk about all of these things. And what we're going to do today, mainly what we're going to do is focus on the paradigm of a 2-level system as an atom. Okay, and maybe at the end I'll get to talk a little bit about the other 2 things over here. Okay? Now, if you want a good starting point for this field and materials to read, these are 2 very light-hearted reviews. They're very recent and very light-hearted reviews that have a lot of very good references that give more intricate details. So if you want a good starting point that is easy to read, these are 2 recommended papers that give you kind of like a nice overview. Okay? But what I want to do in the time that we have are basically 3 things. What we're going to do today, I hope we're going to finish that up today, is number 1. On the slide here, this is basically, I'm going to show you how to engineer these atoms from circuits. How we go from, I just told you in words, we take capacitors, inductors, and so on, and it becomes these level systems. Okay? So I'm going to put, rigor a little bit of rigor behind these words and explain how we engineer circuits and how we get artificial atoms. Essentially, how do 10 to the 23 atoms behave like a single artificial atom? And then I'm going to show you how to couple them to light and get the Jaynes-Cummings Hamiltonian. Okay, so this is the first step. This brings us to the picture of a circuit inside a cavity. The only difference is it's not flying atom, it's just sitting there, immobile. It can't move. It's sitting there on a chip and it's stuck in this cavity. Afterwards, we're going to talk about how to control these two-level systems, how to measure them, and how to do couplings between them. Okay, essentially, a pretty much parallel discussion to what we had with the cavity QED, only what it looks like here. And then, depending on how much time we have, we'll talk about more advanced stuff, encoding information, error correction, and how is this field, how do you look forward, or how would you think of realizing actual, real, useful quantum processors? Okay, that's it. So I hope you'll enjoy this. Okay, so we're going to start with. Are there any questions, by the way, about the flow, about what we're going to do, and so on? No? Okay, great. So we're going to start with circuit quantization, and I will do it as rigorous as time allows, but to be more rigorous, I put a citation here to a review paper that goes into more details than what I'm going to show you. But the underlying assumptions of the certain quantization, okay, if you just take a wire and the capacitor and put them together, you will get, a damped oscillator, right? The charge will flow backwards and forwards, right? Take this charge will flow backwards and forwards here until it will dissipate away, and you will get dynamics of a regular damped oscillator. I'm sure you've solved this equation before. Now, when we do the circuit quantization, and when we're talking about these systems, we have certain underlying assumptions. One is, first of all, we're working at very low frequencies. We're going to work at gigahertz frequencies. These are low frequencies, and what it means is that all the electrons are flowing together. Okay, so you can think of them as something rigid that is flowing from side to side, or is flowing somehow in the circuit. Also, the wavelength, and this is gigahertz, is much larger than the circuit elements that we're talking about. So the wavelength is much bigger than the capacitor. So we have some circuit element over here, and the wavelength is much bigger than that. This is called the lumped element approximation. Okay, essentially, speed of light is infinite here. Everything is flowing together. There are no plasma waves or things like that being excited inside. The second thing that we're going to assume is that dissipation is negligible due to superconductivity. Okay. So I just realized something. Does everyone know what a superconductor is? Is there anyone here? Could you just do like a little red X if you don't know what a superconductor is? Okay, there are only green V's and some people did not answer. Okay, so we all know what a superconductor is. Great. Now is your chance to do an X if you don't know. All right, great. So below a certain transition temperature, we have this zero resistance, and the zero resistance is true at DC and at very low frequencies. Okay, so this is our underlying assumptions for the certain quantization. And now what I'm going to do is I'm going to define for you what are called dynamical circuit variables, which is basically the flux of the circuit and the charge of the circuit. Now you've seen this before, probably, in some course, but just to be explicit, I want to write it down so it's easier for you to flow. So suppose that we have some element over here. You can see the board, right? Suppose that we have some element over here, and this element has some current flowing through it, I. It can be I like that. Okay. And it has some voltage over it, V. Now, the voltage across this element is defined by the integral So, we're going to integrate from this point to this point. So let's call this point A, this point B. So integral from A to B of E R and T dot dl. Okay, so we're basically integrating the field from one side to the other. Okay, so this is V of t. I of t is the integral in a loop around this element of B of R and T ds. And the energy of such an element is basically the integral from minus infinity, where let's say the energy is 0. You can also write here t0, but at t0 the energy is 0, to some time t. Then you have V of t prime, I of t prime, dt prime. And with these definitions of V and I and the energy, you can understand what I wrote here on the presentation, where phi, so the flux degree of freedom, is basically the integral over time over V of t, and the charge, the dynamical variable called charge, this is basically the integral of the current over time. Okay. Now, what I want you to picture in the moment, and we're still classical here, okay, just to keep you, no, we're still classical here. What I want you to picture is a harmonic oscillator over here. Okay. And this harmonic oscillator is composed of two elements. One is the capacitor, this is what you can see here, and the other is the inductor. That's what you can see over here. Now, the assumption about a capacitor and inductor is that basically, for a capacitor, the voltage is basically a function of charge only. And you've seen this, right? For an inductor, the current is basically some function. It's not the same f, so maybe f is going to be, it's just a function of just the flux. Okay, so this is how we define a capacitive element and an inductive element. And if you take these definitions, you can calculate the energy stored in a capacitor and in an inductor. Okay, to be a little bit more specific, if you think about this harmonic oscillator, then it will have some plus q charge here and minus q charge over here. And over here, you can think of some flux phi going through this harmonic oscillator. Okay, so the charge is kind of flowing backwards and forwards, backwards and forwards. And the energy stored in this inductor is exactly this phi squared over 2L that you can see. And the energy in the capacitor is just going to be q squared over 2c. Okay. Now, the voltage, as you know, you can see from the definition, the voltage is simply phi dot. It is also L I dot. And with this relation, what you can do is you can define basically the equations of motion. Okay, this is just like you do it in classical mechanics. You've done this, Hamilton's equations and so on and so on. And you can write the Lagrangian, and then you can go from that to the Hamiltonian. And if you write a Hamiltonian for the circuit, you will get what is written down here, H equals 1 over 2c q squared plus 1 over 2L phi squared, where this is a harmonic oscillator, right, a regular classical harmonic oscillator with a resonance frequency 1 over square root of 2L. So up until this point, are there any questions? Was everyone following what I was doing? I want to see that here everything is. Sorry, I just want to see that everything is in order. Here. Okay, great. So we have no questions. Okay, so the next thing we want to do, now that we kind of understand what is going on and what is the definition of this Q variable, where is it? Q and phi over here. Now that we have these definitions, we go ahead and we do what we do in quantum mechanics. We quantize. How do we quantize?
Impose
canonical relations, exactly. All right? Or in the common language, we put hats. Okay? We write commutator Q phi, we put hats, and we assume that it equals I phi. I think this needs to be minus I phi. The way I defined it here and the way I have it in my notes here, it's minus I phi. So I think I have a mistake in the presentation. Okay, never mind. It's minus here, but that doesn't change the physics at all. And if we impose those, then we can write the same Hamiltonian. We just put hats on Q and phi. We can write them. But we can also take this next step and define the lowering and raising operators. Okay, just like you did when you quantized the harmonic oscillator. You got to some p squared plus x squared. You put hats on them, and then you quantize them into raising and lowering operators. You can do exactly the same thing here. And then you can have Q, and it's related to A and A dagger basically through the 0-point fluctuations. So you have the 0-point fluctuations of Q, the charge, and 0-point fluctuations of phi, the flux. Okay? And you can also calculate and see the variance. So this is the amplitude of the 0-point fluctuations of the charge and flux. And what I did here, I put down some numbers that maybe can relate a little bit better to what we saw in cavity QED. So if you take an oscillator which you plan to be at around 10 gigahertz and has an impedance of 100 ohms, impedance in this case, Z, the impedance is going to be square root of L over C. We don't have any resistance. The impedance is purely imaginary, so it's a reactance. It's a reactive impedance. And it's square root of LC. So just for these example numbers, the 0-point fluctuations of the voltage are going to be 300 nanovolt, which again, this is not small, this is pretty large. And the 0-point fluctuations of the current are going to be around 3 nanoamps for the numbers I gave here. These are not small currents and not small voltages. Okay? It means that there's an opportunity here to get really strong interactions between these things and cavity fields.
What do you mean by 0-point fluctuations?
So when you take a field and you quantize it, remember you have your half photon. Remember when we talked about quantizing the field? You're left with this half photon. This half h bar omega is typically left there to remind us of that. Of course, you can always remove it because it's just a translation of energy, but it's there just to remind us that because of the commutation relation, you're always left with fluctuations. It's basically a consequence of the uncertainty principle. Okay? So you have x and p. Think about x and p as two axes in phase space. You're never defined in a single point in this x space, right? There's always a variance. There's always an uncertainty. Okay? So even at zero temperature, there's always these 0-point fluctuations. Okay? these are the same 0-point fluctuations which are responsible, you remember, for the Lamb shift that we saw. To get a rigorous and better understanding, you really got to take some more rigorous quantum optics course or light matter interaction course and so on, like that. But that's kind of the answer that I can give you within our few minutes that we have. Okay? But any variable, any dynamic variable that you will have once you quantize, because you imposed these commutation relations, you're going to have 0-point fluctuations. And the 0-point fluctuations basically tell you what is the variance of this dynamical variable. Okay, so you can see here I calculated the 0-point fluctuations of the charge with respect to the vacuum state of this oscillator. Okay, you can do the same on V and I, and that's how you get these numbers. Okay, so this is how you go from circuit elements, a capacitor and an inductor, with this definition, to having a quantum harmonic oscillator. Also, what you can see is that a simple LC circuit is like an electromagnetic field. So if you think of a laser, the field of a laser, you can always replace the field of a laser with an LC circuit. You can replace a cavity with an LC circuit. So cavity doesn't have to be a physical cavity, like some material with a physical hole inside. It can also just be an LC circuit, a printed LC circuit. And as you will see in these, in the more advanced lectures, you can use both. So you can take these circuits, which you will see, the nonlinear circuits, and put them in actual cavity, a physical hole inside a material, let's say a physical aluminum cavity, or you can just make another circuit element, which is an LC oscillator, and couple between them. So those are two ways of realizing your quantized harmonic oscillator, your light, either with a physical cavity, a hole in a material, or a printed circuit. But it's exactly the same. Okay? But so far what we saw is that if you take an LC circuit, you get a harmonic oscillator. Now this harmonic oscillator has equal level spacing. It's good for realizing light, but it makes it very difficult, or if that's the only thing you have, you cannot realize a qubit with it. Okay, we already talked about this. If you come and you radiate it with light, in this case microwaves, that are resonant with some transition that you pick, it is also resonant with all the other transitions. Okay, so it means that you cannot create Rabi oscillations, for example, between G and E. As soon as you start pumping, suppose that you start in G, you will start climbing and climbing and climbing, and all that will happen is that you will create this coherent state. Okay, it's this driving of light, okay, just like we saw before. So our purpose is we need something to break this linearity, and this is where the Josephson junction comes in. Okay, so the purpose of the Josephson junction, which is the additional element, which you cannot create in regular metals, you need a superconductor, and I will explain that in a second, to create this nonlinear element. So this goes back to, remember, we're using superconductors, one, so we have no dissipation, but the second reason is that you can create this thing called a Josephson junction, and it gives a circuit element, this is E over here, which has an energy of a cosine. Okay, before, with the capacitor and inductor, if you can see over here, see the energies, the energy of the inductor went like phi squared, and the energy of the capacitor went like q squared. This is what got us our harmonic oscillator. We need higher orders in order to be able to get something that is unharmonic. Okay, and the cosine is exactly that. Okay, it's an unharmonic function, and that's it, and it will give us the exact ingredient to break this harmonicity. I'm using the word harmonic way too much. It's losing meaning by this point. Okay, so the gist of this element is like this. So the Josephson junction is basically a sandwich of a superconductor, insulator superconductor. It is what is drawn here. So we have two superconductors. And in superconductors, the charge carriers are not single electrons. Does anyone remember what they are? All those who voted yes to superconductors.
Cooper pairs.
Cooper pairs. That's right. We have Cooper pairs. Okay. And what the Cooper pairs do, they tunnel from one side to the other. Okay. So each superconductor is going to have its own phase, and the superconductors tunnel from one side to the other. And in just a moment, I'm going to give you some toy model to explain how this Josephson junction gives us a cosine potential rather than just the regular tunneling events that you would get in a metal. And this story will eventually lead us to what is written over here, and it is the simplified circuit idea of how it works. But I really want to give you a little bit of details onto how to think of a Josephson junction. So this is a toy model, and it's just to give you an idea of what is going on, or at least some intuition as to why a Josephson junction gives a cosine potential. Now, if you want to be really rigorous, you can go to Tincom's book, Introduction to Superconductivity, and read there. It is a very thorough book. You will not find the explanation that I'm giving here. This is an alternative explanation that I took from lecture notes of someone else. But the idea here, maybe I'll go to those notes that I have. No. Okay. So the idea with the Josephson junction is like this. So if you consider first, I'm just going to remind you of regular tunneling. And in regular tunneling, some of you might have seen this, suppose that we have a metal. Okay, so the x-axis, think of the x-axis as the density of states. Okay, the x-axis is the density of states, and the y-axis will be energy. Okay, and now in a regular metal, you have these filled levels. They're filled all the way up to here. And now suppose you have some insulator, and now you have another metal, and you put some voltage so that your Fermi energy, your Fermi levels are not the same. And what is going to happen is an electron is going to tunnel through, but it can tunnel to a whole continuum of other levels and then get scattered. So the model that you can give to this thing is basically some capacitance due to the insulator over here and a resistor, right? The electron tunnels from a single level. This is the key point. It's tunneling from a single level to a continuum. And when you tunnel from the single level to a continuum, you get the squaring of the amplitude. Okay, you can think of it as, in the quantum sense, as a measurement. You go from single level to a whole continuum of levels. So you've performed the measurement, so you're squaring the amplitudes. This is where the Fermi-Golden's rule comes from. Okay? And then this tunneling thing simply behaves like some resistor. So this is reminder of regular tunneling. Now for a superconductor, so here you're going single state to continuum. For the Josephson junction, what is happening is that we have a superconductor. So here we have a superconductor. Now the superconductor, we said the x-axis is density of states. So let me write this. So the density of states will go like this. Here it diverges. Here we have, this is the condensate where the Cooper pairs sit. Here we have 2 delta. And here again, the density of states diverges. And these are all filled states, like this. So this is our superconductor, and we have another one like this over here. Okay, like that. This is the condensate, and so on. And what is happening is that you have tunneling from this condensate of a pair into this condensate. So here you have a degenerate level. Remember, this is many, many, many Cooper pairs condensed. Each Cooper pair is a boson, and you have this bosonic condensate. So you have many, 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 many levels. And you're going from one degenerate state to another degenerate state. This is the tunneling. So instead of going from a single level to a continuum, which then results in the squaring of the amplitude, now you're going from a single state to a single state. Okay, from a degenerate state to a degenerate state. Okay, so there is no squaring of amplitude. In this case. And what you can do is you can construct a model. Maybe if I move to the next board over here, you can construct a model which is similar to a tight binding model for this. And because you've solved tight binding and you know it's a cosine, this is why we take this level. But basically, your Cooper pair is tunneling from one electrode, one superconducting electrode, to another superconducting electrode. And what we're doing right now, we're going to, for the moment, ignore the capacitance. And if we have no capacitance, all that happens is that we have just a tunneling energy to go from one side to the other. Okay? So you can define these states, let's call them M. Okay? And again, this is a toy model, okay? But it works pretty well, and it gives a very, very good description. Okay? So you can define these states M, and M is going to be the number of Cooper pairs tunneled. Okay, so it's the number of Cooper pairs that tunneled from one superconductor to the other. Okay? So you can define M as NL. NL is the initial number of Cooper pairs on the left side, okay, minus M. Let's say they tunneled, from the left to the right. They can also tunnel from right to left, but then it's negative. And R, the right side, plus M. Okay, so this is the state M. It just means M number of Cooper pairs tunneled from one side to the other. But because this is degenerate, we just have degenerate energy levels. They're all the same, with some amplitude from hopping from one state to the other. So we can give this model, we can think of this chain where each site on this chain is this number. So this would be M equals 0. No Cooper pairs tunnel. We start from some situation. And this is, Cooper pair tunneled left, and this is one Cooper pair tunneled right. And this is 2 Cooper pairs tunneled left. And so on and so on. And the energy to hop is just some tunneling energy. So you can write the tunneling Hamiltonian for this thing as minus Ej over 2. Ej over 2 is exactly this tunneling energy to go from one site to the other. Sum over M. M plus 1 plus M plus 1 M. by the way, this EJ, if you want to relate it to physical numbers, it equals half h over 2 e squared, 1 over Rn. Rn is the normal state resistance of the junction times delta, which is the superconducting gap. And now if you look at this Hamiltonian and this model, this is just a tight binding model. Okay, so you can define some wave vector phi, and this is exactly the phi that we're going to get in the energy phi, and it's exactly related to the phi current, right? The phi dynamic variable that we defined before. So here we have this lattice with a lattice constant 1, and let's say some wave vector phi, and if I define it like that, then you can define the state phi as being the sum m equals minus infinity to infinity e to the I m phi m. So these are exactly the plane wave solutions that you get for a tight binding model. And the solution for ht phi is basically minus ej cosine phi. Okay? And this is how you get the cosine potential for the Josephson junction. Okay? So this is the shortest explanation that I found that gives, in my perspective anyway, the most intuition as to what is going on here and why you're getting a cosine potential when you have Cooper pairs tunneling from one side to the other. Basically because of the degeneracy of the two condensates on the two sides of the tunnel. Okay. How much? Oh, okay. We're basically out of time, so let me just finish up the slide. So you have one superconductor and another superconductor, and we saw the derivation of the energy, and phi is basically the phase difference between these two superconductors. Okay. And with what I showed you, basically, you can derive what is written down here. This is the first Josephson relation, and this is called the second Josephson relation. Okay. If you look in books, typically the chapters start with, and Josephson said 1, and Josephson said 2. Okay? It's like the 10 commandments, so the 2 commandments. Okay? And Josephson said 1 and 2. Okay? But from these two, you can actually derive this thing over here. And what it shows you is basically that if you look at V, typically the voltage over a circuit element is just the inductance times I dot, where L is a constant thing. But here, L is not constant. So you really can see where the nonlinearity is coming from. Now V is not a linear function of I dot. Okay, it is a nonlinear function because L also depends on I itself. And this last equation is what I like to call the Josephson engineer's relation, because you can ignore everything I told you about the physics and superconductivity and just go to a book or go to this presentation or whatever and see, oh, okay, a Josephson junction is just an inductor that depends on the current, and this is the function. And if I take the critical current of the Josephson junction and take it to infinity, then this is just a constant inductor. But if the critical current is finite, or which is typically it is, it can be anything from nanoamps to microamps, then you get a nonlinear inductor. And now you can understand where we get some nonlinearity. And next week what I'm going to do is I'm going to start by explaining how this nonlinearity creates the unevenly spaced levels and how you can play with it to get different types of atoms. Well, we're going to focus on one specific one just to give as an example. Okay, so are there any questions? Okay, great. If not, I'll see you next week.